Hello everyone, my name is Sebastian and this presentation is about SQuAT-Vis, a visualization tool that we developed to support architects in software architecture optimization. We developed it in the context of the SQuAT project. However, it is conceptually not bound to SQuAT. It can be used together with almost any software architecture optimization approach as long as the technical requirements are met, meaning that we currently use the Java Socket API for data import, and there's only an importer for instances of the Palladio component model. Before I go into more detail about SQuAT-Vis, let us have a look at the domain of software architecture optimization. First, there is the software architect. Let us call him Santiago. Santiago wants to optimize his software system. He just has to pick one of the existing software architecture optimization approaches out there. He has to provide an architectural description of his initial candidate and some optimization goals. As a result, he gets one or even multiple proposals, their architectural description and response values showing the goal satisfaction. Several tasks can or have to be performed by Santiago. First, if multiple proposals are made, he has to choose the best candidate. He could also participate in the optimization process and select candidates for the next iteration in order to steer the search. He also has to decide whether to continue the optimization or accept the proposed solution. If there is a solution, he still has to implement the solution, and therefore he has to figure out what changes have to be applied to the initial candidate. And finally, the result itself is often not enough. Santiago must have trust in the solution and probably wants to get new insights. For example, he wants to know which changes had which effects, and which goals are in conflict with each other. The problem is that software architecture optimization approaches do not care much about how to present the results to architects like Santiago, making his tasks time-consuming or even practically infeasible. So what architects do, and that is also how we did it in the SQuAT project, they create plots to visualize the response values or use generic visualization tools. But that requires effort and at least some skills in visualization, and often the results are not fully satisfying. For the architecture, usually graphical modeling editors are used, but they can only display one architecture at a time, and as you can see in the screenshot, already this can be quite chaotic. That is why we decided to investigate visualization and interaction techniques to display both the architecture information and response values, and implement these techniques into a tool. How did we do that? We first had a look at other state-of-the-art software architecture optimization approaches to identify common use cases in the domain. And this resulted in the 4 use cases that I introduced in the motivation. Next, we thought about which information needs to be displayed to support architects in these use cases. Then we created paper prototypes and discussed them with the members of the SQuAT project team. This resulted in the 3 views which I will show you in the tool demo part. These views are implemented in JavaScript using the visualization library D3, so the front-end can run in the browser of the architect while the back-end is running on a Glassfish server. We also conducted an expert user study and a scalability analysis to evaluate the tool. More information about the prototypes and the evaluation can be found in our paper and the supplementary material. SQuAT-Vis relies on 2 essential concepts. Groups can be used by the architect to categorize candidates, while tags display properties of candidates. The current group is just for visually highlighting candidates, the mark group is for bookmarking interesting candidates, and the selected group contains the currently best solutions. Candidates in the comparison group can have individual colors. There are also 3 tags to highlight the initial candidate, Pareto optimal candidates, and candidates that are suggested by the software architecture optimization approach. Next, I will show you SQuAT-Vis and how these concepts are implemented. The purpose of this view is not only to give an overview of the population, but also to make patterns and dependencies between goals visible. The matrix on the right shows plots for all combinations of 2 goals. Plots in a horizontal line have the same goal on the y-axis, and plots in a vertical line have the same goal on the x-axis. A magnified version of one of the plots is shown on the left. You can decide which plot should be displayed by right-clicking in the matrix. Let's select this one. The circles represent the candidates and are located based on the utility values. Candidates of the active level are colored black, and parents are colored gray, but text can influence how candidates are displayed. Candidates in groups can have other colors as well. Marked candidates are colored in dark blue and selected candidates in purple. Highlighting can be restricted to marked or selected candidates. All the plots also allow highlighting candidates in an area by brushing. The edge of these candidates is colored in light blue. A yellow arrow shows how the candidate evolved since the last level. A different representation for the highlighted candidates is shown at the bottom. These radar charts should help to see the strengths and weaknesses of each individual candidate in a much more compact representation. In contrast to the population view, this view rather focuses on the visualization of individual candidates. In the displayed radar charts, each axis represents one goal. The circles on the axis are located based on the utility values of the candidate. You can hover them to see the actual value. This means that a circle at the outer ring represents a fully satisfied goal, while a circle at the center means unsatisfied. In the list on the right, each candidate has its own card. The behavior is quite similar to the list in the toolbar. It uses the same text, you can open almost the same right-click menu, and group candidates by clicking at the star in the top left corner. Even the search is the same. Besides, you can also use the drop-down menu to filter the list, and a left click groups them as current. As you can see, the visualization on the left now also displays these candidates. The difference is that it always shows a whole group and not individual candidates. This representation is, therefore, better suited for comparison of candidates. The visualized group can be selected in the drop-down menu above. Here we see the current group. And now we switch to the selected group. Switching to the comparison group also changes the colors of the candidates, which makes comparisons even easier. This view is designed to explore the architecture of the candidates. The visualization on the left shows the system's components and their dependencies. These visualizations do not show the architecture of a single candidate, but of all candidates in a group. The radius of the circles and the width of the links indicate how many candidates contain the element. We can get the exact number by hovering over a component or dependency. The force-directed layout allows us to drag components to other locations. It also moves the drag components to the front. Right-clicking a component or dependency will group all its candidates as current. For example, right-clicking the payment system groups the before-mentioned 26 candidates. The now visible pie charts allow for a rough guess about the number of candidates that contain this component. All candidates with the payment system do not contain payment system A or payment system B. The allocation graph on the right shows us to which server a component is allocated to. Circles are again the components, rectangles are servers, and lines represent the allocation. Here we can see that some components are allocated differently by different candidates, while others are allocated at the same server every time. Interaction works the same as for the component's visualization. The visualization on the right shows the system's resources. You can right-click on a resource's name to highlight its server and the other resources at the server. Each of the lines in this visualization represents one candidate. The lines are not fully opaque, so covered lines are still visible. Right-clicking a line will group the corresponding candidate as current. Like the previous two views, the architecture view also has a special comparison mode. The colors allow you to see which candidate contains which element. You can also use the Reduce Graph feature to hide elements that are contained by all shown candidates. In this presentation, I introduced SQuAT-Vis, which is intended to support architects and software architecture optimization by visualizing candidates based on response values and architectural information. Our evaluation indicates that several hundred candidates can be displayed efficiently. The experts performed well in selecting candidates and deciding on whether to stop the optimization. However, they also stated the architecture view to be unintuitive. We have to revise this view and consider further improvements suggested by the experts. Improving the scalability is necessary as well. And finally, integrating SQuAT-Vis into other approaches than SQuAT could help software architects and show whether SQuAT-Vis is as reusable as intended. Thank you for your attention.